Hey everyone, my name is Arian, and today I'm going to present our work called Cache Me Outside, a new look at DNS cache probing. This work has been done in collaboration with researchers at UMass Amherst, the International Computer Science Institute, Citizen Lab, and Boston University. Before getting started, let's review what DNS cache probing is. We know that the DNS protocol is used to resolve domain names to IP addresses. So when a client sends a query for example.com to a recursive resolver, the resolver first checks whether it has the record cached. If the record is not cached, it then contacts the root and then .com, and finally contacts the authoritative name server for example.com to obtain the IP address. When the recursive DNS resolver receives a response from the authoritative name server, it will cache the DNS record for example.com for TTL seconds. DNS cache probing is the process of sending DNS queries to a DNS server in order to find out if it has a specific resource record cached. This can be done by setting the recursion desired flag set to 0, which asks a DNS server to only respond if it has the resource record cached. So here, if the prober gets a response, it knows that the record was cached. There have been a lot of previous studies that have performed DNS cache probing, where they either assume direct access to the DNS server or use OpenDNS resolvers. But nowadays, more and more of these resolvers are configured to only respond to queries from local clients. So the techniques from these prior approaches are becoming increasingly less applicable. Our solution to this problem is DNS forwarders. DNS forwarders are intended to only respond to DNS queries from within the LAN. If a DNS query includes an external domain, then the forwarder will send the query to a remote DNS server. Many of these forwarders are improperly firewalled and also will forward external DNS requests to the ISP's recursive resolver. DNS forwarders are also available on consumer NAT or gateway devices, so they can provide a DHCP lease to clients before the gateway itself obtains a DHCP lease. In the rest of this talk, I'll describe in more detail how we use these DNS forwarders for cache probing. This is the roadmap for the rest of the talk. I'll first talk about revisiting DNS cache probing by leveraging DNS forwarders, then I'll briefly talk about one case study. Let's start with discussing how we locate DNS forwarders. We begin by extracting the results of a DNS scan from the census dataset every day. These scans send a recursive DNS query for a scan domain to the entire IPv4 address space. The name server of the scan domain will always return two answers. One, a fixed IP address of the scan domain, and two, the source IP from which the name server received the DNS query. Next, we process the census results and filter out IPs that did not respond with two correct answers, where one answer is our control answer. Then we try to exclude shared DNS servers, such as Google's public DNS server or OpenDNS. There exist some DNS forwarders that forward to resolvers that do not respect the RD equals 0 flag. This means that they will recursively resolve any request sent to them. But as we're only interested in DNS forwarders that forward to resolvers that respect the RD equals 0 flag, we set up our own scan domain whose name server is configured exactly like the census scan domain. We try to filter the IPs from the previous step by sending DNS queries to our own scan domain. We include forwarder IPs that have these three conditions. First, the IPs that respond to a DNS query with RD equals 0 to a unique subdomain of our scan domain with 0 answers. This is because we don't expect any resolver to have a unique subdomain of ours in their cache. Second, the IPs that respond to a recursive DNS query to a unique subdomain of our scan domain with a resolver address and an approximately full TTL equal to our scan domain's TTL value. And finally, the IPs that respond to at least one RD equals 0 request for google.com with an IP in Google's AS. So now that we have access to these well-behaved DNS forwarders, I'll describe how we perform our DNS cache probing. We developed DMAP using Google's Go Packet library. We provide a set of forwarder resolver pairs, a list of domains, and a list of excluded IP ranges to DMAP. From the set of forwarder resolver pairs, DMAP tries to have two active forwarders for each resolver at any point of time. If a forwarder goes offline or doesn't satisfy the conditions we described before, then DMAP stops using it and activates an additional forwarder that points to the same resolvers. DMAP sends a DNS query packet for each domain name to each active forwarder every interval seconds. And at the same time, the DMAP is sending DNS queries with RD equals 0. It is listening for DNS responses to infer when the DNS record was added to the cache. Furthermore, DMAP continues probing our scan domain on each forwarder to determine whether each forwarder still satisfies the conditions. I'll start talking about the validation of DMAP. So we perform a two-part ground truth experiment using 1,000 RIPE atlas nodes that send recursive DNS queries to a single subdomain of our scan domain. At the same time, we use DMAP to probe for the same subdomain across 16,000 forwarders. So this way, the RIPE atlas nodes would populate the DNS caches of the resolvers, and we would check if we could infer the time of those requests using DMAP by performing DNS cache probing on a population of DNS forwarders. We first compare the log timestamps of our name server with the timestamps inferred from DNS cache probing. And then we compare the query times from the RIPE atlas nodes with the timestamps inferred from our DNS cache probing. And we found that our inferred timestamps are accurate to 5 seconds for 97% of the resolvers. I'll now begin to discuss one case study that we were able to do using DMAP. Our first case study is about locating internet filtering devices sold by NetSweeper. These devices are marketed for use in schools, libraries, and corporate networks, but they've also been used to block political and human rights content in several repressive countries. Previous work has localized these devices by scanning for their admin login pages associated with NetSweeper and looking for NetSweeper block pages. However, these attempts may fail to detect devices configured to drop internet traffic rather than inject block pages. We can perform DNS cache probing to localize these devices because NetSweeper devices communicate with NetSweeper servers to download a set of block lists. This is done using the FreshND daemon that contacts NetSweeper's update domain. We consider a backend to have a NetSweeper activity if there were cache hits for the NetSweeper update domain on at least 6 out of the 7 days of our scan. This table presents some of our results, and you can find more about them in our paper. In conclusion, in this paper, we revisited DNS cache probing since having direct access to DNS resolvers is less feasible, and nowadays, more and more DNS resolvers are configured to only answer to local queries. We developed a system that uses DNS forwarders to perform cache probing in the absence of open resolvers. And finally, we demonstrate that DNS forwarders are effective to perform DNS cache probing via 2 case studies. Thank you for listening to our talk.